Okay, so I think I've got everything fixed, or at least I've got something working right now. I'd like to get something a little better before the summer. But right here, I've got everything working, I think, for the headset. So we'll see how that works out here today. Although I probably won't be moving around quite so much as I did previously. Um, so I'd like to talk about this book today, Matrix Groups for Undergraduates by Kristopher Tapp. I like this. I like this book, and I like it because going around trying to figure out, sort of group theory has been fairly difficult on your own. So this was the first book that actually made sense to me, at least. And there are a couple of reasons why things didn't make sense. One is because when I'm talking about symmetries, normally when I've been thinking about symmetries, I think about them in terms of materials. That's my training. And so when people start talking about SU2 or SO3 or some other symmetry group like that in particle physics, I don't really know what those are. Right? I mean, you can figure out kind of what they are, but I don't really know what to do with them. The way I know how to work with the crystal structures, and those are all symmetry groups as well. So I've got a completely different book on things with completely, all talking about all the different symmetries in different kinds of crystals, just about the crystallography, and it's completely different. I may have two or three of them because I was working in that for a while. Um, so I've got many books that talk about, groups in quantum mechanics, but I never really got an idea about what the groups were other than they were these sorts of symmetries. And I thought this book in particular was pretty good at that. You'll notice it's part of this student mathematical library. It's volume 79. Let's see, how many do they have here? Usually they have a list somewhere. So back here, they have a list. It looks like just back down to 58 here. I think most of them are in print. There are a lot of them. There are many, many good ones. I'm sure many of them are kind of bad. You'll probably see some more later on. And I'm not sure if all of them are, but I think this one was, something that came from a summer school at PSU. They might all come from a summer school at PSU. So I'm not exactly sure how they work. At least some of them did. Another one that I like very much, which is, I think, 33 miniatures, which is 33 really short lectures on quantum mechanics, or not quantum mechanics, linear algebra. So this book talks about matrix groups. These groups that basically can be represented by matrices, and it goes through, an introduction to matrices, fairly simple matrix operators, maybe a little more than most people have seen in their junior year of college, but still, I mean, it's all fairly basic. Then he talks about all matrix groups are real matrix groups, and you'll notice here he's talking about complex matrices are real matrices, quaternionic matrices are complex matrices. Now, quaternions were invented by this guy named Hamilton in the 19th century. Hamilton is the guy who gave us the Hamiltonian, which is so important in your junior level mechanics class and in your later mechanics classes and in all sorts of things later on. It's a Hamiltonian mechanics is a really powerful tool that physicists use and even mechanical engineers use. A lot of the things that we learned in junior level physics class, classical mechanics, I met mechanical engineers who were doing the same sorts of things, learning the same sorts of things as graduate students. In fact, I've got a great book from a guy named Stan Jones, who's at the University of Alabama, about dissipation in those systems. Now, the most interesting thing about it's one of these books that I checked out from the library several times. So my rule was if I've checked a book out from the library 3 times, then I probably ought to buy it. Right? I probably ought to just buy it. Yeah, I'm going to use it a lot. Although usually after that, I don't ever use it. Maybe I refer to it a little bit, but I don't really use it the way I was. Now, the funny thing about that one was the chair of the Department of Physics was Stan Jones, but this was by another professor that was in mechanical engineering. So we had 2 Stan Jones doing work that, was interesting like that. So quaternions are sort of like doubly complex numbers, right? So for a complex number, you'll remember you have a plus ib, right? And that would, give you a point on the plane, basically. That basically gives you a point on the plane. Hamilton wanted to extend that because they didn't have vectors at that time, so that you could have a similar kind of thing for doing 3D physics as you do for 2D physics. And it turned out that the way he tried to do it was to invent something called the Quaternion, which is more or less putting a complex number in for A and a complex number in for B. And then you end up with, an A plus IB plus JC plus KD, where K would be I times J. So you basically end up with 2 different complex numbers and some algebra that goes between them. And I think that there's a little bit of choice in how you develop the conjugate for the quaternion, but I don't really know. And so that gave you IJK as, these 3 different complex numbers that indicated 3 different spatial directions, and then you had 1 extra number. And it never really worked out very well. People used them, but it didn't work out very well. But you might remember from your elementary physics class, your x direction was always I hat, your y direction was always b hat, j hat, and your z direction was always k hat. And that's the reason why they use those. It's all historical. It doesn't mean anything. Although I guess you're allowed to move them around with, those i's, j's, and k's. And then you have absolutely no idea what those i's, j's, and k's mean unless somebody actually defines them for you. So then it actually starts talking about these groups in chapter 3. And a group is sort of a little algebra, right? So, well, I mean, it's not an algebra, but a group is a set where you have an operation on that group that's closed. And you could think about this like if I had a triangle, I could flip it. What would it be? 120 degrees left or right. And I'd have the same triangle in a different orientation. And the different orientations of those triangles would be the members of the group. And the operation would be twisting it. That's the basic idea. So when we come over here to see what he's talking about for all these matrix groups, turns out right here, where are they? And of course I've lost it. There we go. He has these definitions. These definitions don't look very strong, right? You have this SO group, special orthogonal, SU group, special unitary, and SL, special linear group. I'm not really sure what that's used for, but these are the groups that they use in particle physics. So it's going around talking about those right away. And this O means orthogonal, right? Like that. U means unitary, and you'll notice that orthogonal groups use the real numbers, unitary use the complex numbers, and then there's a symplectic group, SP, and that's for using H, which is the quaternions, not the octonions. There's one more group, the octonions, and I'm not sure if they'd work out with all of these things. I suspect so. I'd have to play around with it or find a reference or something like that. So I'd have to probably play around with it. Probably a good idea for me to go through this. So, you know, even though I've got, you know, all these notes sitting in here, it's obvious when I went through this a little earlier that there's a lot of things that I'm missing. So I'd like to go through it again. So then he starts talking about the topology of all these matrix groups, and there's a lot of topology going on in here. So we've got the topology of the matrix groups, and then he's going to talk about the matrix groups as manifolds. This is important, especially for the kinds of things that you might want to use these for in particle physics. So it's very, very useful to get some sort of idea about these things. He talks about the Lie algebras, right? Not just Lie groups, but the Lie algebras, and the matrix exponentiation. And I'll go out there. I'm a little disappointed in this. So I don't think this was one of the books I went to, but, you know, I remembered the definition of matrix exponentiation right here. E to the a is equal to I plus a plus 1/2 a squared plus 1/6 a cubed, and so on, right? This power series representation of e to the a, I think it's a Taylor series. This guy I remembered, but I was reading another book. I wanted to look at another book called Symmetry Methods in Differential Equations, so I could figure out how to use symmetry methods with differential equations. And in one of the early chapters, they said, well, here's how you, so here you have to solve this with your matrix exponentiation. And this doesn't end up being very useful for that, unless, you know, you're doing something approximate on the computer or something like that. You see, we're not really getting the real thing here. So I was really confused. Now, I didn't look at this one. I looked at, you know, more mathematical sort of texts. Well, I shouldn't say more mathematical, more analytic text. This is a very mathematical text itself. But I'm sure that I'm supposed to be able to figure it out from some of these problems. There are problems for each section. And I'm sure by looking at these problems, I should have been able to, figure that out by looking at what's going on in here. But, you know, I just spent an hour wandering through this chapter, and I wasn't able to. So this looks like exactly what you need to, this problem here looks like you need to find, use the sort of calculus or the calculation, do the calculation to find this e to the a, or at least that's what I would have done to solve it. And to do something like that, I'd want to use the method where you find the eigenvalues of the matrix A, and then you add up, that whole thing, which you can do. You find those eigenvalues, eigenvectors, and all that other fun stuff. You just need the eigenvalues, I think, which for this guy is not hard, right? You can see the eigenvalues off the top of your head just by looking at this particular matrix. But you need to know that you're using those eigenvalues. So I actually found a really old book that may have been sitting around here in my collection that explained it simply, right, and didn't try to go through that whole matrix exercise. And it's this thing, because I remember using them in the past, and but the only thing I remembered was that power series representation. So I remembered that power series representation. I did not remember how to really calculate it, because who cares about the power series, right? If I want to actually solve this differential equation thing with it, I need to actually calculate it. I don't need a huge weird thing that shows up from the summation. And then you talk about the Lie bracket up here. Well, matrix groups are manifolds. We sort of talked about that. We talked about the Lie bracket. This is something that you'll find very familiar, right? More about manifolds. Just look at it here. What do you see? Well, you see the Poisson brackets, right? You see the uncertainty here. So this is something that you'll see a lot in both the commutation relations, I guess is the way I'd say it. So you see the commutation relations for quantum mechanics, right? Sx comma xy is equal to IH bar SZ, right? For spin, for example. Or xy is equal to IH bar Z, or something like that. So, you're talking about these guys don't commute. And that's very, very important, right? So this is something you want to use. I think I just said that wrong. But for the spins, I remember those calculations. So these guys sort of define quantum mechanics right there. So those uncertainty relations and the Poisson brackets, those are important for symmetries in classical mechanics. And maximal tori. So you have some different things about toruses, manifolds, and roots. And I tried to go over the roots again right there. So again, I thought this was pretty useful. I should have looked at this. Why study matrix groups? Four-dimensional topology, particle physics, and Yang-Mills connections. Obviously, particle physics stuff, graphics programmers. Those quaternions end up being useful there. Differential equations, the theory of differential equations, which I've never actually looked at. I've done some differential equations stuff, but never looked at the theory. Shape of the universe, quantum computing. Quantum computing has these huge weird matrices if you want to look at it. Maybe I'll pull out one of those books later on sometime. Linear algebra and Riemannian geometry. So those are all fairly interesting. You need only the following prerequisites for this book. Calculus through multivariable calculus. So calculus 3, linear algebra, abstract algebra is a little bit different, and analysis, which is more or less advanced algebra, so that, or not advanced algebra, advanced calculus. So that's more or less building calculus from nothing, which is a lot of fun. So if you have a chance to take a class like that sometime, you probably should. I didn't have a fun time in my abstract algebra class, I'll say that. Although I've got some books, some abstract algebra books that are really interesting. The class itself had a few issues, including the professor died in the middle. So that's matrix groups for undergraduates. So if you want to learn about matrix groups, because you're interested in particle physics and stuff like that, I think this is a good way to start. It's nice and simple, and it's not sort of backbreaking. A lot of the other books that I've looked at, even if they're fairly good after you figured them out, are not very good before you figured them out, right? So I won't mention any, but there are a couple other books that I read before I read this one that were a little more complicated, although that were a little more complicated than this one, although I thought they did a reasonably good job. They just didn't really introduce what the groups were as well as this text does. So if you want to get an idea about what those groups are, I think this text does a good job. If you want to get a good idea about how the groups are useful, I think some of these other texts are important, but it might be worthwhile figuring out what they are before you try to figure out how to use them, right? Okay, so I think that's enough for today, and I'll pull something else off the shelves next week. Bye now.